Welcome to Module 5.4. The time has come to look at filters from the frequency domain perspective. And the starting point is this amazing result. If you take a complex exponential and process it with a linear time invariant filter, what you get at the output is a complex exponential at the same frequency as the input. Only the phase and the amplitude may have changed. This has all sorts of interesting implications when we consider the Fourier representation of the elements involved in a filtering operation. We will derive what is called the frequency response of a filter, and we will use that to classify filters in the frequency domain. We will also revisit our friends the moving average, the leaky integrator, and even the Kaplan-Strong algorithm, and see how they fare in frequency. Welcome to Module 5.4 of Digital Signal Processing, a module in which we will look at filtering from the vantage point of the frequency domain. And to do so, we will introduce the concept of eigensequences, which despite the fancy name are just complex exponentials. We will derive the convolution theorem after having obtained a frequency representation of filters, and then we will look at frequency and phase responses of filters we know. What happens if we take a linear time invariant filter H and we use as the input a complex exponential of known frequency omega 0? Well, let's write out the convolution. Then we exploit the fact that the convolution is commutative, and we exchange the order of the terms in the convolution product, at which point we can start writing out the convolution sum explicitly, and we have the sum for k that goes from minus infinity to plus infinity of h of k that multiplies e to the j omega 0 n minus k. Now we can take out the constant term that doesn't depend on k out of the sum, and we have a leading term of e to the j omega 0 n that multiplies the sum for k that goes from minus infinity to plus infinity of h of k times e to the minus j omega 0 k. But now this guy here, we know very well what it is. It's the DTFT of the impulse response computed in omega 0. So it's big H of e to the j omega 0, which multiplies our original input e to the j omega 0 n. Hence the name eigensequences. Just like an eigenvector is a vector that, when multiplied by a matrix, gives a scaled version of itself, an eigensequence is a sequence that, when input to a linear time invariant filter, returns the sequence itself times a scaling factor, which happens to be the value of the DTFT of the impulse response at the frequency of the input. So the first fundamental property that we can glean from this derivation is that a linear time invariant system cannot change the frequency of a sinusoidal input. And so, since the sinusoidal input is a pure frequency component, it's clear that the DTFT of the impulse response fully determines the frequency characteristic of a filter at a given frequency. Let's examine a little bit more what happens when we process a complex exponential with a linear time invariant filter. If we write the value of the DTFT of the impulse response at omega 0 as a times e to the j theta, where a is a real number and theta, of course, is an angle between minus pi and pi, if you will, then we have that the processed complex exponential is the original complex exponential, which has been scaled by the amplitude a and has been delayed or advanced by a phase term theta. So if a is larger than 1, then we have an amplification. If a is less than 1, then we have an attenuation of the input sinusoid. And the phase shift, again, if it's bigger than 0, then we have an advancement of the sinusoid, and if it's less than 0, then we have a delay. The convolution theorem tries to generalize this result by asking the question, what is the DTFT of the convolution of two sequences? Or in other words, what is the DTFT of the output of a filter? The intuition here is that the DTFT reconstruction formula tells us that any signal is made up of infinitely many sinusoidal components of the form x to the e to the j omega times e to the j omega n. And if I were to process a single sinusoidal component independently via a filter H, I would get a value like so, h j omega e to the j omega n. So I wouldn't be surprised if the DTFT of the convolution of two sequences was just the product of the Fourier transforms. So let's go see how we can derive this more formally. If we write out the DTFT of the convolution of two sequences, well, we can write out initially the formula for the DTFT, which is the sum from n from minus infinity to infinity of the value of the convolution in n times e to the minus j omega n. Then we expand the formula for the convolution inside of the DTFT summation, and we get a double summation over the indices n and k of the convolution product here times this complex exponential here. In the next step, we do a little trick whereby we add and subtract k from the argument n. So instead of putting n, we write n minus k plus k. And in so doing, we manage to split the complex exponential in two components here that we will distribute across the summations. So now here we collect the terms that do not depend on n, and here we put the rest. This first term here is the DTFT of x of n. That's really easy to see. The second term looks like a DTFT. We might be confused by the fact that the indices here and here are n minus k instead of n, but the fact that the index n ranges from minus infinity to plus infinity makes this term completely irrelevant. And so, indeed, we have the product of two DTFTs, the product of the DTFT of the impulse response times the DTFT of the input. The Fourier transform of the impulse response is called the frequency response, and just like in the case of the single complex exponential, we can split the significance of the product in the frequency domain by separating the effects of the magnitude and those of the phase. So the magnitude of the frequency response will determine whether certain frequencies of the input signal are going to be amplified or attenuated according to whether the frequency response is larger than 1 or smaller than 1 in magnitude in certain frequency bands. The effects of the phase are a little bit more difficult to qualify right now, but it will be clearer later on that the phase will determine whether the signal will conserve its shape in the time domain or its shape will be altered. Let's go back now to our friend the moving average and compute its frequency response. The moving average has an impulse response, which is just the indicator sequence for the interval 0 to capital M minus 1 divided by capital M. We have already computed the DTFT of such a signal in module 4.7. If we consider now the magnitude of the DTFT, we find out that it's just 1 over capital M that multiplies the absolute value of sine of omega over 2 times M divided by sine of omega over 2. An interesting thing to remember is that the magnitude response is going to be 0 at multiples of 2 pi over capital M, except in 0. So here you see that you have indeed capital M minus 1 zeros along the frequency axis. We can plot the magnitude response for increasing values of capital M. So for instance, here you have the frequency response for M equal to 20, and you could count the 19 zeros along the frequency axis. And here you have the frequency response for capital M equal to 100. And you can see that the frequency response is very concentrated around the origin. We will see the significance of that later on. Let's go back to our denoising example that we studied in the time domain in the previous module and look at its development in the frequency domain. So remember, we had a smooth signal. Here we're talking time domain. So we had a smooth signal that was corrupted by some additive noise that we represent here in orange. In the frequency domain, the spectrum of the smooth signal looks like this. Most of its energy is concentrated around the low frequency, so it's a low pass signal. And the Fourier transform of the noise looks like noise in the frequency domain as well. So when we put things together, we have the spectrum of the smooth signal, we have the spectrum of the noise, and the sum is the noisy spectrum of the measured signal. When we use a moving average to filter this noisy signal, in the frequency domain we're multiplying this spectrum by the frequency response of the moving average. And in magnitude it looks like this. So here we're using, for instance, a 9-point average, as you can see from the number of zeros along the frequency axis. So the product in magnitude determines a very deep attenuation of the high frequency, and therefore most of the noise that was contained in these bands has been eliminated. At the same time, though, if you compare the result of the filtering operation with the original spectrum, you see that the filtering has eliminated parts of the original spectrum that actually had every right to be there. So that proves that there's no free lunch in signal processing as well, and in order to remove the noise, sometimes you have to remove some of the good part with it as well. Before we move on, let's look once again at the same denoising operation in the time domain, now that we know what's going on in the frequency domain. And we can see that when we use a moving average of, say, length 12, we are indeed smoothing out the highest components of the noise, but not so much the ones that are slower moving, and that we are already starting to alter a little bit the curvature of the signal, as explained by the spectrum we just derived. So what about the phase? The best way to understand the effects of the phase on a signal is to distinguish three different cases. The first one is zero phase, which means the spectrum is real. The second case is linear phase, where the phase is proportional to the frequency via a real factor d. And the third case is nonlinear phase, which covers all other possibilities. To understand what phase does to a signal, let's take a very simple discrete time signal made up of the sum of two sinusoids. X of n is equal to 1/2 sine of omega 0 times n plus cosine of 2 omega 0 times n. So it's two sinusoids at frequencies one double of the other. And the sum looks like this signal that we plot here in this graph. We can call this signal a zero phase signal because the phase associated to each sinusoidal function is zero. Now let's add a phase term to each component and make sure that the phase is proportional to the frequency of the sinusoid. So what we add is theta 0 to the first component at frequency omega 0, and we add 2 theta 0 to the second component whose frequency is 2 omega 0. The value of theta 0 is actually irrelevant. But we can see that when we add a phase term to the sinusoidal components that is proportional to the frequency of the sinusoid, the net effect in the time domain is just a shift of the signal. The shape of the signal remains exactly the same. If now we add a phase that is non-proportional to the frequency, so in this case we change the phase to the first term to 0, and we leave a phase term of 2 theta 0 to the second term, while the frequencies of the two components have not changed, the shape of the signal in the time domain has changed significantly. Please note that in all three cases, the spectrum of x of n remains exactly the same in magnitude. To understand that the linear phase term is simply a delay in the time domain, consider the following system where we have a filter D that simply produces a delayed version of its input. The input-output relationship is this one here, and in the frequency domain we can take Fourier transforms left and right, and we obtain that big Y of e to the j omega is equal to e to the minus j omega d times big X of e to the j omega. This is really equivalent to saying that the frequency response of this delaying filter is simply e to the minus j omega d. So again, we have a linear phase term where the phase introduced by the filter is proportional to the frequency via a factor d, which actually represents the delay in the time domain. In general, if we can split the frequency response of a filter into the product of a pure real term and a pure phase term, it means that the filter operates by combining the action of a zero phase and therefore zero delay component that only affects the magnitude of the input, followed by a delay by these samples. And this delay is inevitable in the case of causal filters, for instance. Let's consider the moving average again. The frequency response is the product of a real term here and a pure phase term here, where the delay d is exactly m-1/2, which represents half the length of the support of the impulse response. And this is indeed the delay introduced by the moving average. So we've looked at the moving average, and by now you know that what comes next is the leaky integrator. And indeed, let's consider the impulse response, which you remember is 1 minus lambda times lambda to the power of n multiplied by unit step, so an exponentially decaying sequence. If we take the Fourier transform of that, we've done that in detail in module 4.4, and here is the result. Big H of e to the j omega is 1 minus lambda divided by 1 minus lambda times e to the j omega. Now, to find the magnitude and the phase of this animal, we need to use a little algebra, and we need to recall this very simple result. If you have 1 over a plus jb, you can always rewrite that as a minus jb divided by a squared plus b squared. So if the number x is actually 1 over a plus jb, the magnitude square of x is 1 over a squared plus b squared, and the phase of x is the inverse tangent of minus b over a. This applies to the leaky integrator in the sense that we can rewrite the frequency response as 1 minus lambda divided by 1 minus lambda cosine of omega, which is the real part of the denominator, minus j times sine of omega, which is the imaginary part of the denominator. And by applying the formula that we just saw, we find out that the magnitude square of the leaky integrator is 1 minus lambda squared divided by 1 minus 2 lambda cosine of omega plus lambda squared. And the phase of the leaky integrator is the inverse tangent of lambda sine of omega divided by 1 minus lambda cosine of omega. So you can see that the phase is definitely nonlinear in this case. If we plot the magnitude, we can see that we have a characteristic that is very similar to that of the moving average, although we don't have any zeros, and the characteristic is monotonic rather than oscillatory. As lambda goes closer to 1, we see that, once again, the frequency response concentrates around the origin, and for lambda very, very close to 1, we have something that resembles the frequency response of a moving average computed over a large number of taps. The phase looks like this. It's a nonlinear characteristic, and as lambda changes, the steepness of the transition between positive and negative phase increases as well. What is interesting in terms of the combination between the magnitude and the phase response is that what interests us is the part of the filter where the attenuation is not too big, because that's where the frequencies will pass through, whereas here they will be fundamentally killed. And in that area where the frequency response has a magnitude that is sufficiently close to 1, the phase is actually more or less linear, so we can use the leaky integrator without incurring excessive phase distortion in the passband. Finally, let's revisit another classic, namely the Karplus-Strong algorithm, and let's try to analyze its behavior using the convolution theorem. Remember, the Karplus-Strong algorithm is initialized with a finite support signal x of support capital M, and then we use a feedback loop with a delay of capital M taps to produce multiple copies of the original finite support signal scaled by an exponentially decaying factor alpha. So for instance, if we initialize the algorithm with one period of the sawtooth wave, what we get in the end is multiple repetitions of that period scaled by an exponentially decaying envelope. In the time domain, we can write this out explicitly as such. Here we have the first period of the output signal is just a copy of the non-zero values of the finite support signal, followed by another copy of the non-zero values of the finite support signal scaled by alpha, followed by another copy scaled by alpha squared, and so on and so forth. The key observation to analyze in the algorithm within the paradigm of the convolution theorem is to see that the output can be expressed as the convolution of the finite support input with a sequence W of n that we build in the following way. W of n is equal to a to the power of k for values of the index n that are the kth multiple of capital M, and it's 0 otherwise. So if I was to draw the sequence, it would look like so. So it would be 1 in 0, it would be alpha in M, alpha squared in 2m, and it would be 0 in between. So a series of exponentially decaying deltas spaced m points apart. With this, we can write the convolution theorem and we say, okay, the output is simply, in frequency, the product of the Fourier transform of the finite support signal times the Fourier transform of the signal W of n. Well, and now we can proceed exactly like in module 4.4. If we consider the example of a sawtooth wave, we know that the Fourier transform of one period is this one, whereas the Fourier transform of the sequence W of n is the rescaled Fourier transform of the exponentially decaying sequence, which means we will have several peaks happening in the minus pi interval. We put them together graphically. We have the Fourier transform in magnitude of the sawtooth period. We have the Fourier transform in magnitude of the staggered exponential sequence. We take the product of the two and we obtain the same spectrum that we derived in module 4.4.